Inverse relation. Given a relation R, we define the inverse relation to R as follows. Whenever there is a pair AB which is related in the sense of R, we reverse the components of the pair. B becomes the first component, A becomes the second component, and the set of such pairs comprises the relation, the inverse relation to R. This relation is denoted by R with the superscript -1. So from this definition we see that A and B are related by the inverse relation if and only if B and A in this order are related by the original relation. Here is an example. If A is a child of B, we could express this equivalently as B is a parent of A. So the relation is a child of is the inverse relation to the relation is a parent of. We're going to consider a simple relation and its inverse relation, and we will show how this relation can be described by formulas or different types of diagrams. So our relation R is defined as follows. X is related to Y if and only if X and Y are numbers, integers between 1 and 4, X is smaller than Y, and X is equal to 3 or Y is equal to 3. How would we define the inverse relation by means of a formula? I'm going to leave the formula exactly the same, but when I describe the inverse relation, I will reverse the order of X and Y. So Y is related to X by the inverse relation if and only if the same formula as previously holds. This is justified by the fact that this expression is equivalent to this expression. And now I can work with this equivalence, replacing every X by Y and every Y by X in simultaneous substitutions. And if I do that, then I obtain this, right? So a Y has been replaced by X, and X has been replaced by Y. Then this part really doesn't change because X and Y play symmetrical roles. Here X is on the left hand side, it goes to the right hand side, and so on. And going beyond this example, if a relation Q is defined by a formula where X is restricted to a set X, Y is restricted to a set capital Y, and where X and Y are expected to satisfy a certain formula A, if I want to define the inverse relation, I will be doing this as I did it in the previous example. So I will reverse, I will put Y on the left hand side, X on the right hand side. Now they are related by the inverse relation if and only if the same formula holds as previously. And the equivalence can be rewritten with x replacing y, or and y replacing x, giving us this. So please notice that in this last formula we have x is in capital Y, y is in capital X, and when we write the arguments for the formula A, y comes first. The same relation could be defined as a set of tuples, and these are the particular tuples that belong to the relation. To form the relation R inverse, I'm switching around the components of the tuples. So the tuple 2, 3 becomes 3, 2. And if you visualize relations as tables, we obtain the following tables for our relations. Now, for the same relation, let us consider visualization as a Cartesian plane graph. The black dots constitute the graph of the relation R. The relation R inverse is comprised of the ordered pairs represented by these circles. It is immediately visible that the two graphs are symmetrical with respect to the diagonal of the coordinate system. Let us consider visualizations as discrete Cartesian graphs. So I'm forming a diagram for the Cartesian product of the set with integers 1 through 4 times the same set, and I'm graphing the relation R using big black dots. Then relation R inverse is graphed using circles. It is immediately visible that the two graphs are symmetric with respect to the diagonal. Let us consider visualizations as directed graphs with loops, although in this case no loops will be used. The relation R is visualized on the left. For instance, the pair 2, 3 belongs to the relation R, and because of this we have a directed edge from 2 to 3. Then we have the pair 1, 3 and the pair 3, 4. When we graph the relation R inverse, the graph looks very similar, but the arrows are reversed. So we had an arrow from 2 to 3 for the relation R. Now for R inverse the arrow goes the opposite way, from 3 to 2. Consider visualizations as domain-to-range diagrams. Relation R is on the left, R inverse on the right. Please notice that there is a symmetry between the two diagrams. And finally, definitions by truth matrices. Recall that in a any matrix, the rows are numbered with integers starting at 1, and they're numbered from the top. So this is row number 1, row number 2, row number 3, row number 4. Columns are also numbered with integers starting at 1 from the left. So this is column number 1, column number 2, column number 3, and column number 4. And a truth matrix allows us to define a binary relation on a set of integers from 1 to n. Also, in the context of binary matrices, we use indexing as follows. A sub I, comma j represents the entry in the row I and in the column j. So, for instance, this would be an entry in the column, in the row 1 and in the column 3. So this is A sub 1, comma 3. And this belongs to row 3 and column 1. So this is the entry A sub 3, comma 1. And the relation R, which we considered in the previous examples, corresponds to this matrix, where the symbol for truth value true is used in the case of pairs which satisfy the relation. This is the entry 1, 3, and 1 is related to 3 in the sense of R. And similarly, on the right, I show the truth matrix for the inverse relation. Let us notice the symmetry between these two matrices. This symmetry is described using some conventional terms used in the theory of matrices. The second matrix is a transposed version of the first matrix. And in general, a transposed matrix is a matrix symmetrical to M with respect to the diagonal. And the diagonal of the matrix runs from the left top to right bottom. So entries A11, A22, A33, A44 are on the diagonal. We call this the diagonal because the other diagonal is not important. And please notice that indeed the second matrix is symmetric to the first with respect to the diagonal. We have the truth value true in here, and after transposition it ends up in here, and indeed there is a truth value in the matrix for R inverse right here. Here's an exercise. I would recommend that you pause the video and answer these questions. And two propositions. Taking the inverse operation twice produces the original relation. Then we will establish how the inverse operation interacts with the complement operation. If you take, let me read it this way, the complement of the inverse relation equals to the inverse relation to the complement. If R1 is a subset of R2, then the same holds for inverse relations. The inverse to R1 is a subset of the inverse of R2. And in the next proposition, we look at the interaction of the inverse relation with union, intersection, and set difference. The inverse of the union of two relations is the union of the inverse relations. The same for the intersection, the same for the set difference.